Okay, let's get started. Hello, everyone, and welcome to this EDSL webinar, From Building Physics to Simulation Outputs, right? We've had a fantastic response to the registration. Several hundred of you have registered, a lot of interest. We've received a few questions already about the topic and the recording and various other things. So I'm very excited to host this webinar once again with the EDSL team. Let me hand over quickly to the speakers from EDSL. We'll start with Andrew, and then Paul, Duncan, and Ian. Hi guys.
Hello, yes, I'm Andrew. I've been with EDSL for about 12 years now, and I'm a software developer with a background in physics.
Yeah, hi there, Paul Bacon, Director at EDSL. Been here for 21 years now. I head up the consultancy department here and take on all the consultancy work that you might want to throw my way.
I'm Duncan MacArthur. I've worked at EDSL for 25 years, and I'm a software developer.
Hi, Ian Heighton, Technical Director at EDSL. I was there at the beginning, 1989, when EDSL was incorporated. So yeah, I've been around a while.
Ian, thanks so much. Such an interesting topic, really, from building physics to simulation outputs, right? I think it's super important. Sometimes we forget that bit in the middle because, we're taught building physics, perhaps at college, university level, and then we use the software for projects, compliance. But, very few people, I think, understand nuances of the building physics, how it's applied in building simulation, what impact that has actually on your building performance, right? This is, the unintended consequences, modeler knowledge, user expertise, nuances of the physics as well. So that's something we'll be exploring today. Let's take a look at the quick agenda. What we'll do is we'll start with the building physics you absolutely must know if you're a simulation user. Okay, Ian's going to talk us through that. It's a great refresher on fundamental physics, something that's super interesting. And then we'll talk about physics and computational methods. A quick overview and comparison, just so you know what terminology means, right? You might hear different types of computational methods terminology being thrown around. Increasingly, you're seeing things like time step turning up in references and standards and guides. What does that actually mean? So we'll cover some of that. And Ian's going to talk about some validation standards and references to be aware of as well. And then we're going to look at where does CFD fit in to this thermal energy modeling. And then we've saved some time for Q&A and discussion at the end, which is where we'll explore the topic of AI and simulation for the built environment. So the EDSL team will be giving their views, opinions, and product development updates. Please post your questions in the chat and the Q&A panel. And if you register for this event, we'll be sharing a recording later this week once we've had time to polish up the videos. Okay, let's jump in, and I will hand over to Ian Houghton.
Yeah. Thanks very much, Nagman. The lady you're looking at is actually Sue Pavey, and this is back in, I think it's somewhere between 85 to 89, and this was when TAS was basically being fully developed. I mean, it started out in Cranfield in the 1970s during an oil crisis that was going on at the time. But this was really when the first big investment into the software was going on. So yeah, it's a nice image from quite a long time ago. Again, if you look back, a lot of this sort of development that TAS has undergone has been driven by regulations and energy requirements, and at the moment everything is all about CO2 reduction. So I think this is why we're seeing quite an uplift in terms of interest in terms of energy modeling again, but it's not so much the energy these days or the cost, it's really to do with the CO2 emissions that people are trying to reduce. And I think all of those factors are driving interest, and as I say, these periods of time where you get these requirements coming down from government, etc., that's what we're all responding to. And I think obviously global warming, climate change is very much on people's agenda. So again, we're seeing another push, as it were. And to finish off our process, we'll look at some recent CFD advances that we've made. There's a previous webinar, is that right, Nagman? We had a previous webinar, didn't we, on the CFD stuff? So yeah, we're not going to go into great details on the CFD, but you can go back and I think check out that one, which has been uploaded. So 1985, around there somewhere. 87, I think, was when I actually joined the original company. EDSL, as I say, was formed in '89. One of the first projects that I ever worked on was the PowerGen headquarters. I think it's up near Coventry. It was quite an innovative design at the time, because it was one of the first fully naturally ventilated buildings. And it was at this juncture that I think it was Ernest Griffiths and Sons who picked up the project. I think it was Rab Bennett's Rab Bennett's and Associates were the architects. Both, very, very skillful professionals, and they ended up coming to us and basically were saying, what's the building going to do when we've got the windows open, because you really didn't have much prior experience doing natural ventilation. So it was that era, late 80s, mid to late 80s, where suddenly we were sort of going, okay, cross-flow ventilation, okay, stack effect. You had to suddenly start taking into account all of these things, and that was the first time we properly fully integrated an airflow network, which basically took account of all the wind pressures, wind speeds, wind directions, gave you that sort of convective point of view, but also included the stack effect, which was effectively being driven by the building simulation. So this was the first time we coupled the building simulation, which is all about fabric and heat flows in and out of walls, etc., but coupled that to a full airflow network, which was obviously being driven by wind speed and direction and the stack effects. So that was probably the first project where we started to get into things like demand control ventilation, etc., and subsequently, obviously, we've got many more features now in terms of how you can control those ventilation functions, mixed mode stuff, etc., which is I'll be honest, that's a real pig of a thing, because you're effectively doing a naturally ventilated model, and then you have to come up with mixed mode, you have to come up with some criteria at which point you turn off the natural ventilation, shut everything down, and actually turn on the air conditioning, which again is another tricky one, to be honest. Solar tracking, again, that was a long way back, and that was very much to deal with the current trend, where a lot of buildings were having a nice, sort of central atrium with a nice glazed roof. This was novel at the time, by the way. You'd have this central atrium with a nice glazed roof, and you'd have offices, on the perimeter, if you like, of the atrium. And frequently you'd get the sunshine coming through that nice glazed roof of the atrium, which makes for a nice airy sort of space, in the atrium itself. But it also means you're going to get solar gain hitting into the offices. Previously, I'm not sure if other software packages do this, but we introduced this solar tracking concept where you could say, okay, instead of just having the solar gain coming through that atrium roof glass, and then it just becomes a heat gain within the atrium, we were actually tracking that solar patch onto the office glazing, the perimeter office glazing, and then obviously the solar gain ended up in the right place, which was inside the office spaces. So we distributed that solar gain a lot more effectively. And again, as I say, driving force for that was project that work that was coming in. I'm pretty sure we were the first DSM to be approved for Part L EPC. I remember a couple of iterations later, through second or third approval process, they started to sort of ban the company that got through the tests first, and just made sure everybody was approved at the same time. But I'm fairly certain we were the first DSM to be approved for Part L EPC. And yeah, Paul lodged the first level 5 EPC in the UK. Can you remember when that was, Paul? That must be going back quite a long time now. Sorry,
yeah, it's 2008. I think it was April time. Like you say, I think they made all softwares live on the same day, but we'd obviously been ready for it, and I lodged the first level 5 EPC pretty much the day it was released, so I was the first.
Yeah, and I'll be sorry, because apologize, because the dynamic CFD is very much a relatively recent thing that we've been working on and pushing. So that obviously is a fairly significant step in terms of being able to integrate computational fluid dynamics with the building simulation, which means rather than just getting an average zone temperature, you've got the ability to see, if you like, within the space and quantify comfort levels, temperatures, resultant temperatures, etc. So that's a fairly significant thing. And the dynamic bit is the fact that you can actually do this rather than just a sort of single snapshot that can take many hours or even days to produce with other CFD packages. We've got a sort of technique, an algorithm, which is much faster, and it allows us to simulate from sort of 8 a.m. right the way through till 4, 5, 6 p.m. not too long. I mean, generally it's quicker than real time, but obviously if you're doing a complete atrium, that's going to be slower than a classroom, for example. But classrooms, you can get quite good results on a course mesh in 15 minutes, 45 minutes. So it opens up CFD to being more of a design tool rather than just being a sort of post-processing event where the design's completely fixed at that point, and you're really just using the CFD to just sort of there's a pretty picture for the client, and it's just oh, that's 2 p.m. on Monday afternoon, and that's it. Whereas at least we can sort of pick perhaps a design day for cooling and a design day for heating and run the entire day, so you can see exactly what's going on those under those design conditions. Yeah, I think that's it, unless anybody wants to chip in with anything else. I mean, Duncan's done a lot of other stuff. We haven't sort of stood still. I know Duncan, bless him, gets all of the regulatory stuff at the moment, which is not a great deal of fun. It's got to be said. Yeah. Okay. Yeah. Sorry, Duncan. Go.
Just happy to move on. We'll come back to it.
Yeah. Yeah. Okay. Great. Yeah, the building physics one, I was just going to say, you really don't need anything other than sort of rudimentary GCSE now. I was going to say O-level, shows my age, but O-level or A-level sort of physics is really all you're talking about in terms of the primary heat transfer processes in buildings. Literally are just conduction, convection, radiation. So conduction, you're talking into and out of fabrics. Convection is obviously hot air rising off radiators or cold air dropping off a cold window, that kind of stuff. And radiation is quite often overlooked. You've got two forms of radiation. This is good, actually. Sorry, the key down in the bottom right is worth a look. So you've got what we tend to characterize as shortwave radiation and longwave radiation. So sunshine, light coming off bulbs, that kind of stuff is what we characterize as shortwave, because it tends to be higher up the spectrum, electromagnetic spectrum. Long-wave radiation is something that often gets overlooked, but if you've ever been to a nice sort of cozy pub on a English winter's day and they've got the fire going, you can feel the heat from like 5 feet, 10 feet away, and it's that long wave radiation that is quite significant within the built environment, both internally and externally. So that fire in the pub, most of the hot air is just going straight up the chimney, but it's managing to heat the space based on primarily long wave radiation. So you can absolutely 100% feel that. A bit like an electric bar heater, for example. That's the same sort of principle. And within the building, you're getting this sort of long wave exchange between all of the surfaces and the fabrics, etc., and the occupants and the heating and cooling equipment. And outside, you've also got this long wave stuff. One of the questions we quite often ask during interviews for people when we're interviewing them for a place at the company is, why do you get frost on your car, when the air temperature stays above freezing, like 1 or 2 degrees, and yet you get this frost on your car? And this is long wave backloss radiation. So basically, if it's a clear night, and you tend not to get this happening when it's cloudy, but if it's a clear night, you're basically allowing long wave radiation to absolutely leave completely and just head off out into space. And it's at that point you can see this reduction in the surface temperature because of that exit of radiant heat, and that's how come you get the frost on your car and the ground frost on the grass, some mornings, and yet your fish pond, for example, isn't frozen over because it's got enough thermal mass to get it through. Whereas these lightweight things, you can quite often get that frost forming on the surface. But that's it really. I mean, it's worth pointing out as well that if you think of the wall, not the infiltration, but if you think of a relatively heavyweight wall, you can actually get the strange sort of, if it's massive, you can get this strange situation where you've actually got conduction coming in from both sides. So if the building's cooled down overnight, for example, and the structure is really quite cool, the heating kicks on inside the space, obviously for the occupants. You've maybe got some early morning sunshine coming in, and because it's thermally massive, you can actually get heat coming into that fabric component from both sides. So it's worth remembering that it's not just heat flows one way or heat flows the other way. Sometimes it can be flowing out from both directions. Sometimes if it's got warm, obviously, and then it's cool inside and cool outside. So it's very much a sort of thermal inertia thing with the fabric, and that's really what all of these systems of calculation are trying to capture, the interaction between the external environment, the internal environment, and the fabric of the building. And on top of that, the air conditioning systems and all of the casual gains that you can see indicated here. It's a nice diagram. We created this, I think, many years ago, but Nagman's made a sort of prettier, more colourful version of it for us. So yes, it's worth a good look.
It's worth understanding these results because they help you. If you look at the TSD file, our building simulator results file, you can actually understand your building performance a lot better by looking at those results, because it shows you these things in more detail for each hour. So you can start to get a feel for what's happening with the conduction, the long wave radiation, the building heat transfer, how much energy is being stored in the air, etc. So it is worth looking at, and you can do that on a surface by surface basis as well.
Yeah, which is not the default. The default is just to chuck out zone information, which is what most people want. But if you want to dig into it, and Alan always refers to this as forensic skills, it's almost like you are a detective trying to figure out what the heck's going on. You can start to turn on lots of surface outputs, so temperatures, heat fluxes, all sorts. Pretty much everything you can take a look at, so you can start to pick it apart. But again, you probably wouldn't do that very frequently. But it's nice to have that opportunity to dive right into the sort of guts of the physics, as it were, and see exactly what's going on in terms of heat balance. And that's really what all of this is about. It's fundamental heat balance. It's a zone heat balance, it's a surface heat balance. That's what the software is doing. It's trying to make sure you've got the temperatures set correctly so that all of the heat fluxes balance out, and you've got conservation of thermal energy, which sounds a casual way. I just say, oh yes, it's going to work out that equilibrium point for all of these surfaces in all of these zones in these massive, great, 4,000, 2,000 zone models. Those are the worst. That's obviously where it gets the trickiest. Plus, of course, you've got the airflow networks bouncing around in there at the same time. So yeah, it's a non-trivial task. Yeah.
Ian, what's interesting about this image and the building physics in general, and one of the reasons we wanted to do this webinar is that there's a lot going on here in this picture.
Oh yeah.
Okay, and we could have put 10 more things in there. Just this is just what we could fit into one diagram, right? So buildings, how we kind of treat buildings as I don't know if steady state is the right word, but there's a bunch of calculations and the steady state. How would you describe, on a spectrum of very steady state to very transient and dynamic, where does a typical building fit in?
Hugely
I
transient.
think that's really interesting. Hugely transient.
Hugely transient. We're going to come on to the other calculation procedures in a minute, which have obviously got simplifications to a certain degree in the earlier ones. But no, Bill, if you think about the way that the weather changes through a day, it's sort of sinusoidal. I mean, it can be -8, it could be -1, it could be you can get massive fluctuations. And certainly, if you think about cloud cover and you think about the way that the sunshine, solar gains, how they can change quite rapidly. We only get we get spot values for external temperature, and we get previous hour averages for things like solar gain, wind speed, wind direction. So an RH is spot value as well. Sorry, by spot value, I mean that's the exact value at noon or 1 p.m. or 2 p.m. Whereas the other gains, like the solar gain, wind speed and wind direction, these weather input parameters, they're all previous hour averages, which is why, people, we're going to come on to this later, but people always go, why do you have an hourly reporting interval? Well, it's because what's the point reporting sub hourly when the input data is hourly fundamentally? So yeah, but that's what we're working off.
Let's look at that now. So the way this webinar has been structured is this is stuff we think people should know or know already. Okay. Now we'll come on to things which you might not know. Yeah.
No, I'm just about to say it. You don't need to know any of this. It's like I did make the analogy to you guys yesterday. It's a bit like driving a car. You can drive a car without any understanding of the internal combustion engine at all, and that's not a problem. Some of the best drivers don't know how the internal combustion engine works, I'm sure, but I tend to think if you understand how the engine is working, then you can probably drive better and
Yeah.
possibly not stress the engine quite so much, or at least, appreciate where the problems might come from, that kind of thing. So this
Yeah.
is, it's not necessary, but I think it's kind of useful information to just put out there.
Yeah, it's useful. I mean, to your point earlier about the forensics and what Andrew was saying about the TSD, to be able to interpret the results, to have a fundamental knowledge of the building physics. Super useful. I saw someone trying to put their hand up. If you have any comments or questions, you can use the Q&A or chat panel, and we'll address some of them as we go along and take the rest later. So Ian, I think from that perspective, moving on, here's things or bits you might not know, right? Which is the really interesting bit and the purpose of this webinar.
Yeah. The first two, to a degree, have come from two different projects. We did a lot of analysis of One New Change, which is a land securities building in central London near to St Paul's. Learnt an awful lot during that process. The three things were infiltration leakage, thermal leakage, and huge quantities of simultaneous heating and cooling. So if you look, I'll start with the third one. If you look at dynamic simulation models, typically you're getting, the 100% heating or cooling through the day, for example, and then at night it drops off to sort of virtually 5% if you've got sort of parasitic power turned on, that kind of thing, but it's virtually zero. Whereas when we looked at the data from One New Change, 100% during the day, and then it dropped to 50% at night. So there's 50% power consumption during the night, which is just, it seemed to me colossally high. Eventually I sort of went, okay, I'll double check this, and went to the national grid where they do actually show you exactly what's being generated and consumed daily. And it's virtually identical. It's 100% during the day. And I think it went down to 40% at night, but it's still, compared to what we're told to put in because of the regulatory calculations, it's still a massive amount of consumption and consequently heat gains during the whole of the nighttime, which explains a lot of these. What's the performance gap? What's the difference? That's a huge difference. That's a pretty monumental one. The second one, which is less significant, this is thermal bridging, edge losses, that kind of stuff. So we obviously do the edge loss stuff, we obviously do the thermal bridging, but in real buildings the construction is usually far inferior to the sort of perfection that is being put into the dynamic simulation models. I often say the DSM model is perfection. It's perfectly built, it's perfectly occupied, it's perfectly controlled, it's perfectly run. But in the real world, you've got, coming on to the third point, you've got different set points, and you end up with simultaneous heating and cooling. And you just don't see that in the perfection of a dynamic simulation model, because that's not what we're told to do. We're told to hold a very clear set point. And yet in real buildings, you've got somebody on one side of the office turning it up, one person on the other side of it turning down. One's too hot, one's too cold, and you get huge amounts of simultaneous heating and cooling in the real buildings. So in terms of what's the performance gap, well, the performance gap doesn't exist. If you put all of the stuff that the real world is doing into your DSM, you get back to within 5-10% maximum. So this 2 or 3 or even 4-fold difference between the perfection of a typical DSM model and the real world is entirely explicable. And one of the biggest ones is infiltration. So in your regulatory calculations, you have to put in a flat fixed infiltration rate. So that's literally everywhere across the building is getting maybe half an air change on the perimeter and a quarter of an air change in the center of the building, the core. But when you look at a real building, if the wind's coming from the east, those east facing zones absolutely get hammered. And the west zones on the opposite side of the building, all that air has traveled through the building, it's got warmed up or cooled down by the plant, and as it's coming out of the building, there's absolutely no load on the other side. And the only reason I spotted this was because at One New Change we were seeing massive disparity between air handling units. I think they had 4, and sometimes one air handling unit would be going mental and the others would be sort of just ticking along. And the moment we put this wind and wind speed based infiltration in, we suddenly started to hit the actual performance that was being seen in those air handling units. So the regulations are fine, you know, they've got to do something. But a big difference between the real world and, you know, what we do as far as the regulatory calculations is this, you know, infiltration, flat infiltration versus calculated infiltration. And obviously the calculated infiltration is based on cracks. Yeah. And this is, I think we've got you've upgraded the utility, haven't you, Andrew?
Yeah, we have a little tool to help you do the wind-driven infiltration. So you can take an air pressure test result, and basically it'll work from an air pressure test result and give you the crack area that you need to apply to your window frames to model these leakages in the facade and throughout the building, so you can get the proper infiltration flow. And this gets you much closer to, if you were comparing against measured data, then you get much closer to reality. It's quite a significant impact that it has. So yeah, definitely the worst way to model infiltration is with the static air change rate. The next best way is with this and the wind-driven infiltration. And then, of course, you could do wind pressure coefficient files, but we found that actually it's diminishing returns, and that our default model for wind pressures is actually very close to what you get when you do a full external CFD simulation anyway.
Yeah. Thanks to Hilson Moran for that, by the way, because they did a full external CFD flow calculation, compared it to what we were doing, and the differences, they weren't huge. So, you know, that's great news from a dynamic simulation point of view. It doesn't mean you've got to spend a lot of time and effort and money, you know, doing external CFD to get pretty decent results. So yeah, very positive. Heat transfer coefficients. This has cropped up. Pretty much all of the software packages, Energy Plus, you know, IES ourselves, I think, and ESP tend to use very similar sorts of. Alamdari Hammond is a convection coefficient model that's used extensively. There are many of them, but one of the things we noticed when we were working with Hilson Moran and Loughborough there was a test house in Loughborough, and then we've also been working with Ballymore with a flat down near Heathrow. And the one thing we're picking up is that overnight, when the air gets really stagnant and there's not really much happening, I mean, the Loughborough house was completely freewheeling, which is unusual. You know, that's an odd circumstance. It's very rare you'll get completely nothing happening in a space overnight. But we've noticed that these heat transfer coefficients actually go much lower. They go well below 2, which is a typical minimum for these models. So we've actually managed to use the CFD and, you know, replicate the environment and do some tests again with the help of Hilson Moran. And yeah, we're hopefully going to, well, we've got a new and enhanced heat transfer coefficient model. It's just a question of making sure it works across a broad spectrum of buildings. The problem we found at the moment is, depending on the sort of room shape and size, you're seeing very different reductions in this heat transfer coefficient stuff. So the model's still very much a bit of a work in process. But yeah, we've also seen as part of this work that you know, the pace at which the heat transfer coefficient changes is also very indicative of how the air's moving in the space. And this might not be an obvious, you know, observation or intuitive. If you've got a stagnant sort of room full of still air and you start to apply some sunshine, some radiator heat gain or whatever occupants, it takes about 40 minutes for the air to get moving to a point where the heat transfer coefficient picks up. You know, that's a big chunk of an hour. So there's not just the lag in terms of the building fabric and its mass. There's also this sort of lag in terms of the air movement and how long that takes to get going, which again is part of the process of trying to improve these heat transfer coefficients to have that sort of slowing down, if you like, or the slow uptake in terms of getting back to a sort of normal or more typical heat transfer coefficient value.
I mean, to get into that situation, you'd probably need, you know, no internal gains either, because they would be contributing to the. So it's quite a you know,
it's a novel
set of circumstances. Yeah.
But again, it's one that we do need to cover, because some buildings go stagnant overnight. It's not that common, as you say, though, Andrew. So it's a not a sort of major thing, but again, part of the work we're doing at the moment, and good to be aware of as well. Yeah. I'm going to hand over to Andrew now for this flow part.
Yeah, just to illustrate, just to give you a sort of visual. Nagman, feel free to play the video there. Just to give you a visual sort of illustration on some of the things that you can see with the CFD that you might be missing out on from just looking at building simulator results. Again, the first thing here, you can see that the temperature of the space is not uniform. So if you were looking at building simulator results, you would get an average air temperature for the whole space. And this can be particularly significant if you've got quite high spaces where you might have an uneven distribution of temperatures, where you've got much warmer air rising to the top, or you've got wind coming in from one particular facade. And what you're seeing here is you're seeing just a classroom where you've got a corridor which gets quite a lot of solar gain, highly glazed. You've got apertures at the top and on both facades, and you've got apertures into the corridor. And as you progress throughout the day, you can see the wind direction changing, and this has quite a significant effect on the temperature distribution within the space. So you've got the buoyancy forces competing with the wind pressures coming from the wind from outside. You can see that when the wind changes direction from a particular direction, it pushes in a lot of warm air from outside, and it has a really significant effect on the mixing in the space. And this is sort of quite interesting because you can help optimize your design here to try and improve the comfort within the space. So for example, when the wind comes from a particular direction, you could actually improve your design in some circumstances by closing certain windows to prevent certain flow paths from occurring, and ending up with a more sort of even distribution of temperatures. And here as well, you can see there are no. So on the right hand side there, you can see a screenshot from the TSD results file. And when you have infiltration, when you have wind coming in and out of the apertures, you see arrows on the apertures. So in these hours that we're looking at here, the external temperature is actually higher than the internal temperature. So those windows have closed, and then when the outside cools down again relative to the inside, and it will be beneficial to open the windows, you'll see that the windows start to open, and again you'll get cool air coming in through the space and affecting the temperatures there. So that's really nice. It can really help you sort of understand the space. And again, when we have our PPD metrics in our CFD, you'll be able to get a much better feel for the real occupant comfort that isn't based on that average temperature, because that can be quite significant, especially if you've got high spaces where your average temperature might be higher towards the top, or here where you've got cooler temperatures generally towards one side of the classroom compared to the other side.
And this was purely thermal control, wasn't it, Andrew? Just temperature based?
Yes, exactly. This is just temperature-based thermal control. Here you can see we're in the evening now, and the apertures have opened again. You're getting a much cooler air from outside coming in and cooling down the space.
Yeah, it's worth pointing out we can do CO2 as well and do them both at the same time. Yeah.
Yes, exactly.
We have a few. We have a few users asking about aperture calc and how to get access to that.
If you just send us an email, I can send that across. There's also the ability to model wind-driven ventilation infiltration in the building simulator as well. There's an option in heating plant room controls in TBD where you can. There's something called infiltration coefficient. You can play with that, and that makes it wind-driven to a certain extent. Yeah. So if you want more details on that, just contact us.
Yeah, it's not as good as having the absolute, here's the wind speed, here's the wind direction. It's going to be coming in from that side, but it does allow you to modulate infiltration based on wind speed. So at least that's a step up. Right, I think Duncan, are you going to take us through the NCM stuff? You're the expert on this bit.
Okay. So the NCM methodology is not without issues. That's what we're saying here. So if you're using the NCM constructions database, always check the material properties and the order of the layers, and make sure that they're always sensible before using them. When we run Partel and EPC calculations, they're sized based on a 0 degrees outdoor temperature, and there's also no margin on the sizing. So you would never use the NCM methodology for sizing your real building. You'd always use, proper Sibsy heat loss day or, dynamic simulation. And there's other things as well with, the fixed level of infiltration. I've got, the number of hours that the system's operating is actually looked up based on the actual activity assigned to the space. So if you do simulate the same building with the the setback temperature and the a certain point during the day, you'll actually find that your number of hours operating in the system will be different to the one used in the calculation. So, and also the flow rates for fans, it won't model things like the turn down of fans for a VAB system compared to a CAB system. So, but all of these things you can model outside of Partel and get a more realistic result for doing that.
Didn't one of the door constructions have a meter of soil on it or something? So Andrew said that.
Yeah, I think it did. Yeah, I think I'm not sure whether in the
Yeah.
latest version, but at one point the door had a meter of soil in it. Yeah, and the order of the materials are not correct in some of the constructions, so that can have a very significant impact on the results.
Yeah. And then there's other things from like the BRE daylight factors calculations. So, it can't model borrowed light. So if you have a null wall between you and a space where there's a window, then it won't account for any daylight being able to pass into that, like through that null wall. So
yeah, it also won't account for external shading at all, the BRE method.
So so you can do a detailed, daylight factor calculation outside of the NCM method. And then there's various things like improvement factors, which you're adding improvement factors to what's actually sort of a perfect model anyway. So maybe they should, I think you can get closer to the real building, following something like Sim 54, that sort of methodology.
Yep.
So yeah, that's it really. So I suppose the most important thing is like never use Partel or EPC for sizing, because it's not how you'd size it for your real building.
Yeah, so true. Yeah, I'm going to pick up the next point in terms of room volumes and wall thicknesses. We don't use psi values, although we're probably going to have to implement it because people seem to want it. What we do is we actually have, as people who've got TAS know, we have wall thicknesses in the 3D modeler. So you can change a wall from 10 centimeters to half a meter thick. And what the 3D modeler can do, which is great, is it can work out an internal surface area and an external surface area. And it will also take into account window reveals, that kind of stuff. At which point you've got both of those values, and what we do is take the average of the two. So you're looking at a sort of a line that's mostly center line in terms of the wall, and we work from those values, which means we obviously increase the internal surface areas, which is what a lot of packages work from and why they need the psi values, but we're effectively doing this geometrically, which I prefer because obviously psi values are fixed, what's per linear meter and all that kind of stuff, perimeter, linear meter, whereas what we're doing is saying, okay, if you change your thicknesses, you're actually going to see the edge losses and the thermal bridging stuff taken account of automatically, which I think is a better way of doing things. But as I say, we're getting some pressure to put the psi stuff in, at which point we're going to have to smash everything down to zero thickness and then use the psi values, which seems a bit daft, but that's that
yeah
one.
Because the room volumes can have such a significant impact on the results as well. So that's why we really prefer to have thicknesses to our building elements. It has such a significant impact, especially in where there's suspended ceilings or high spaces.
Oh yeah, ceiling voids are huge. Yeah, and particularly if you're running air through them at night, that kind of stuff, then they need to be zoned and treated separately. But yeah, generally speaking, you're right. The floor ceiling ones are pretty massive. Yeah. I don't know about appropriate zoning where external shading is involved. I'm guessing this is our external zone thing where you're putting loads of shades outside. Is that about right,
it's
guys?
important. So what we're really saying here is it's important to remember that when you assign a zone to a space, it's important to try and make sure that a zone represents a homogeneous parcel of air, where you're not experiencing vast differences. So, for example, if you think about a room and you zone it near a window, you'd expect that the temperature near the window might be higher. It's receiving, daylight's getting more solar gain. So it's not representative. That area is not representative of the whole space necessarily. And this particularly applies to atrium zoning as well. So again, with NCM, you don't zone vertically. You have to ensure that you have the same zone vertically. But if you're doing an overheating analysis or doing a proper analysis, you can use different zones vertically and see the stack effect. And you can see that in the TSD file. You'll see the stack effect, and you'll get you get
the right temperature gradient. Yeah, exactly.
Yeah, exactly.
It's going to be hotter at the top. I can guarantee you that.
Yeah.
that's a given.
Yeah, exactly. And that's something that you can capture by zoning appropriately. And it's the same as well with things like external shades. Sometimes you see people using very large external shades all the way around the building when really they should be split up, because again, you're going to get different, wind pressures, solar gain. Yeah, exactly. So that's it's quite important to understand how to zone properly.
Yeah, and just the two diagrams on the left, I'm moving to the next point. People always say, U value, that's the sort of metric that we're going to try and match up to. Well, these two constructions, I think the top one is almost pure insulation and the bottom one is pure concrete, but I've played with the thicknesses, so they end up with the same U value of 2.67, and you can see there's a massive difference in terms of the dynamic response and also the magnitude of the response for these two materials. So matching a U value does not mean you're going to get the same thermal performance from a particular construction, and even matching the G value won't really help you. So it's important to get, as we've been saying, it's important to get the layers of materials correct in that construction, because just matching to a U value, you can get the right answer for the wrong reasons, and that will change your results really, really massively.
Yeah, it's like you said, Ian, it's like a mile per gallon figure.
Yes, sorry, that's in my notes, but I forgot. Yes, exactly. So you've got a standardized test to give you miles per gallon in, what is it, motorway, A roads and city centre driving, and great. That's a standardized test, which is what the U value is, because those are standard conditions, as you pointed out earlier. But in the real world, when you've got obviously dynamically varying conditions, then you're going to get very, very different performance from those very static values that have been. So using U values as an input is just crazy in my point of view. From my point of view, it's just bonkers.
Yeah, and it's not just the thermal mass either that has an impact when you're comparing two materials that have the same U value. The order of the materials, where you put your insulation layers. You can have two materials with the same U value and the same thermal mass, but have different performance depending on the order of the materials. So again, this is why it's so important.
Quite right, actually, because the example I wanted to give was, if you've got the insulation on the outside of a concrete wall, or you've got the insulation on the inside of a concrete wall, identical U values, but my God, the performance is radically different. The insulation on the outside is just light years better, because the inside space has got access to that thermal mass. So that's a really good test if you want to do a very quick and simple one. Insulation on the outside or insulation on the inside on a simple concrete cube, you'll see a very rapid difference. Yeah, marked difference, and yet it's the same U value. Yeah.
And the time step point brings us nicely on to computational methods, Ian.
Yes, yeah. We often get this. Oh, TAS uses an hourly time step. Well, no, we don't. We just happen to report the results hourly. We're actually doing conduction transfer functions. So if you want to dig into it, Laplace transform solution of the Fourier heat conduction equation, it's all out there on the internet. Effectively, it's an analytical solution. So it's a bit like. There is no time step. It's continuous. It's all based on derivatives, which are fundamentally continuous. So we're picking up all of that dynamic process through, and this is the only way. And again, I would advocate go and do the TM33 tests. Use whichever software package you currently have. Do the conduction tests in TM33 if you can. I think we're coming on to this.
Let's look onto that methods one.
Yeah. Okay, admittance, I'm not an expert on this, and I'm not entirely sure how SBEM does it, but it basically does an energy balance per month. So that's 12 calculations compared to 8,760 for a DSM. Admittance was an interesting thing that SIBSI came up with, which was primarily created as a hand calculation, and this basically assumes that you've got sinusoidally varying weather or flat weather. So in the summer they'd have a sinusoidally varying infinite amount of time, but it allows you to come up with a sort of, it's not a steady state result because obviously it's got the sinusoidally varying summer temperatures. In the winter they generally just stick in -4, -6. Paul, is that about right? Is that a reasonable sort of assessment of what Admittance was doing? Because you're the Sibsy guy.
Yeah, exactly that. That's what our design days were, wasn't it? So we did the repeating design day for the summer and the steady state -4 for the winter.
Yeah, so it wasn't. It was dynamic in as much as it's a sinusoid, but it was an infinite sinusoid. So you're effectively getting to a kind of steady state based on a simplistic sinusoidal weather pattern. Whereas we found that we get hot patches in the UK, but they don't go on forever, sadly. So that's a pretty massive overassessment. Resistance capacitance networks not really done anything with these, but I mean the resistor is effectively trying to represent the conductance of the entire construction, and the capacitance is trying to represent the mass of it. So it's a bit like a resistor and capacitor in series, if you take an electrical analogy. And sorry to say, I think thermal analysis has borrowed quite a lot from electrical engineering over the years, many times. Finite difference, for me is a bit of a, it's a clunky way of doing things, because you're just putting in large numbers of nodes into a piece of fabric, and then you have to take really quite tiny time steps to get there. So again, I'd say go do the TM33 tests, particularly the conduction tests, and see what you're getting, particularly for lightweight structures. Finite difference will have trouble picking that up in terms of accuracy. And you've also got the speed side of it. You've got to put a lot of nodes in there, and it's not an analytical solution. This is a bit like comparing Newton-Raphson to find the root of a quadratic equation, for example, which obviously you've got to, gradient, go up again, gradient, go up again. There's a lot of computation to get close to the answer, whereas if you've got the quadratic formula, that's about 10 floating point operations and you've got the exact answer. And that's the difference, because as I say, it's a Laplace transform solution of the Fourier heat conduction equations, which is why conduction transfer functions are just so much better. I'd go with room response factors here, but I think the next slide covers a lot of that. And the final bit, sorry, just go back if you wouldn't mind, Nagman. The final bit, which is, at the moment we do one-dimensional heat conduction through these surfaces of a zone, and we can couple that with the CFD modeling, which is here and now. Ideally, what we'll do eventually is we'll have a full solution of the heat conduction in 3 dimensions for the fabric, and then the only thing we'll be pulling in from the building simulation will be the adjacent zone air temperatures. At the moment we're pulling in surface temperatures, then doing the CFD, whereas eventually we hope to be able to do the full thermal analysis of the actual fabric in 3 dimensions. Sorry, Nagman, you go on there. How are we doing for time? Oh shoot.
Yeah, we need to pick up the pace, I think.
Yeah, well, I think I've covered most of this, haven't I?
Yeah.
So
this was just it was a quick overview of the computational methods that Ian was talking to in the previous slides. So you can see the method here, and this is our opinion of some of the key strengths around accuracy, computational cost, limitations as well. So what Ian was saying is conduction transfer functions down here. This is where EDSL task is. And what's interesting is, Ian, a couple of questions have come in. Right,
they do exactly the same thing.
So a couple of questions have come in. Is EDSL the NG Plus engine? Maybe you should just clarify that.
Oh, definitely not. Totally independently developed. E Plus was, is it Lawrence Berkeley and DOE, Department of Energy in the United States? So if you look at the Energy Plus engineering reference and you look at our theory manual, you'll notice incredible similarities between the two. The one thing I don't understand about Energy Plus, because it uses the same conduction transfer function sort of ideas, the Z transform stuff, state space stuff, I don't quite understand why it's so slow, but I think that's because they've coupled the building to the HVAC modeling side of things. So it's almost like the HVAC modeling side of things slows stuff down, whereas we've stuck very much to you do the building simulation, you get your room weighting factors, and then you go and do your HVAC simulation. People either love that or hate that, but it's much quicker.
Yeah. To summarize, the TAS engine is independently developed by EDSL.
Yeah.
And it's proprietary, and it's it's homegrown engine basically. One of the fastest 100%. Out there. And talking about, you mentioned standards and references, Ian. Let's finish on this, and then we'll move on to the CFD.
Yeah, well, TM33, it's well worth a look. It's a really good document. I don't know why it's been deprecated or whatever it is. It says superseded on the CIBSE website, and there's nothing that's superseding it. So it's well worth a look. And the conduction tests, as I say, the ones you can see on the right there, was it G3.2? Those dynamic conduction tests are well worth a run through. I mean, TM33 was originally designed as a user test. I mean, it's been sort of used as a software validation test, but the idea was that, you know, engineers could use their software of choice, go through the problems, hit the known results from all of the four, you know, vendors, you know, all the four software packages, and they would then have confidence that they could use the software appropriately across a large and broad range of problems. So, you know, that's a really good thing. ASHRAE 140-1 is interesting because it's not a prescriptive test. You just do the runs and you don't have to hit certain bands, whereas TM33 you have to hit the bands. So 140-1 is very useful and very interesting, but we use it for internal testing between releases to just make sure we haven't chucked a bug in there. 13791 is not so much of interest to most users, I would suggest, but that's where the concrete cube came from, basically. And AM11, I thankfully know very little about AM standards. So anybody else want to jump in with AM11?
Yeah, it's more of an application guide on the best practice of using building performance. But I think the key point here was the CIBSE TM33. It's definitely something, if you're a building performance, building simulation user, and you consider yourself an expert, you should be familiar with that, is what Ian's saying. That's your kind of viewpoint. You should be able to replicate those tests independently in the software that you're using for everyday projects.
Absolutely right. All four vendors were sat around at Arabs, and Mike Holmes was the kind of chairman of the whole thing, which was great because he had experience. I don't know if he's still going, but he had experience with. They had an internal tool called Room, and you had all four of us. Like I said, you know, IES, ESP. E+ were represented by Design Builder and ourselves, you know, and all four vendors sat round, thrashed through these tests and managed to get within 0.6 of a degree and just a few percentage points in terms of energy consumptions and other values. So, you know, it's impressive. You got four totally independently developed engines giving you very, very similar results once we all sat around and agreed it.
I think, Ian, one point we might have skipped over on the conduction transfer function methodology, like EDSL, is its resilience to large models, large and complex models, right? How good it is, and
not sure that's
calculation.
I'm not sure that's so much to do with the conduction transfer function as the internal algorithms that try and balance the thermal and the airflow network. So the airflow network is highly unstable. So how you link that airflow network calculation to the building thermal analysis calculation is very sensitive. And if you get it even slightly wrong, you can just end up ping-ponging backwards and forwards between the two. So the airflow network says, I've got to stop telling people technical things, but you can end up pinging backwards and forwards. You know, the airflow network says, no, the air's got to do this, and the thermal goes, no, okay, you do that, and then I'm going to change the temperatures. And once the temperature changes, then the airflow changes, and you can end up in a very unstable situation. So making sure that converges and converges in a reasonable space of time is tough. That's tough, and that's way too much detail for everyone, apart from maybe three of us.
It's a great segue into CFD, and we've had several attendees ask this question. So where does CFD fit into thermal and energy modeling? You've alluded to it already in some of the previous
at the moment
comments.
Is the quick answer.
Yeah,
yes.
But this, what we're sharing on the slides here, this is feedback collected from the industry. We did multiple surveys, or EDSL did multiple surveys, and this is actual feedback from all of you. You might have seen surveys going around by email, on LinkedIn, and various other sources. So this is real feedback from the industry, and the response to that was dynamic CFD and ambience 3D. And maybe, Ian, we could spend a minute just on that.
Yeah, by all means. Basically, if you look at most CFD packages, the commercial ones like Fluent, etc., they use a thing called pressure correction. So mass conservation is a tricky thing with the Navier-Stokes equations. That's as far as I'm going to go. Don't have to turn off. But what we've come up with is a sort of neat way of eliminating pressure. I think I'm allowed to say that, which means we've got a lot more stability. We're not using pressure correction. And another fundamental feature of it was the fact that it's 100% stable. So we can literally, I mean, this model we're looking at here, you can literally run your building simulation as long as you've got the surface output specs to give you the temperature and the aperture flows. Nat vent projects you can do really, really quickly. You can literally just pull the TSD information in. It'll grab the geometry from the building simulation file. It will just set it running. You pick a day and you say which hours you want, and it will literally just run from 8 a.m. through till 6 p.m. I'm very aware we're running out of time, and this has all been covered in that previous CFD webinar. So if anyone's particularly interested in this, I'd say go back and take a look at the CFD webinar.
It's on YouTube, and we can share that link again with everyone.
I'd share the link again. Yeah. Don't want to kill too much time on that because it's been covered. Yeah.
Okay, does anyone else want to add anything here? Maybe Andrew, Duncan?
Yeah, I mean, it's really, again, the main focus is just to make it really accessible to people, because CFD prior required quite a lot of expert skill. You know, it needed expert skill in specific tools, but also understanding the physics, because some of these other tools, because of the methodology they use, they can produce unstable results, unrealistic results, and you might not necessarily spot when things aren't right. Whereas, you know, we take away that requirement for all that sort of expert skill set and make it much more accessible, and actually give practical result metrics at the end that you can use to inform your designs. So that's the key takeaway, really. But I'll save some time for questions, I think.
Yeah, let's get onto some questions. There's a training course coming up. I'll let Duncan jump in here as well. 11th May. Go ahead.
There's still time to book on the training course, the next training course, which is held in Milton Keynes, and it's from the 11th of May to the 14th. So if anyone's interested in some in-person training, there's still time to book on the course.
Yeah, there's a link there. We'll share again in the follow-up email on how to book onto that. We've got a few minutes left. We'll do a quick fire around here and be quite specific. Thank you, everyone.
I was about to say 3 minutes ain't much, is it?
Not for a question this big, but thanks for your questions, everyone. We did have a technical question from Doug. This is going back to ceiling thicknesses and separate zones. How do they compare with the NCM floor-to-floor zoning rules in the way you should do it, or how TAS does it?
Pass on that one. I'm afraid my NCM knowledge is scant. So yeah, thanks, Duncan.
Yeah, I mean, you would model the ceiling thickness as a building element thickness. So if you had a ceiling void that was 600 mil, you'd have a building element for the ceiling that was 600 mil, and then that reduce the volume of your space, of your zone.
And also adjust the surface areas, which is a good point.
Yeah. Outside of NCM, you could actually model that void as a zone. You know, if we had a meter void, you might want to model it as a zone. It could be a plenum or something, moving air from the zone to that plenum and out, something like that. So you may want to model it in more detail outside of the NCM.
We have a related question on how the wall thickness in the model relates to the wall thickness in the TBD, and the understanding was that wall thicknesses in the 3D model wasn't that relevant other than volumes.
No, it's the 3D wall thickness is very critical, because that gives you the correct volumes and the correct surface areas. That's the key bit I was talking about with the edge loss stuff. The construction in TBD is not checked in terms of its thickness to match up. So you can have a wall in 3D TAS that's half a meter thick, and you could put like a construction that's a piece of paper onto that, but the paper construction would only be applied to the area that's been calculated and sent through. So that's the difference.
A question on dynamic CFD. How can someone access that for their projects? Quick response, and we can follow up in the follow-up email as well.
Consultancy only at the moment.
Yeah, we're hoping to release it end of the year, early next year, perhaps. We're still working on it. So at this time, we're just testing it internally and using it for consultancy projects to improve it before we release it.
Yeah.
So if anybody has any consultancy needs, if anybody has any consultancy needs, if you just contact us, then we can carry that out for you, whether it be normal dynamic simulation or CFD.
last, should we just have a quick comment from each of you or whoever wants to jump in on the role of AI simulation for the built
Oh
environment, or
God,
specifically
here we go.
maybe specifically for TAS and EDSL, where you see that
Yeah,
going over the next 1 to 3 years? Yeah.
I'll give you the specific TAS EDSL stuff. Andrew can back me up on this. I must admit, I've been around long enough, 64 shortly. I've seen loads of fads come and go, and neural networks are phenomenal. I've used them, I've trained them. They're very, very useful gadgets, but it's the usual thing. There's loads of hype around neural networks where people are trying to apply it to nonsense. The two areas I'm particularly interested in is floor plan recognition, because they're incredibly good at recognizing patterns and structures. So, if we can get rid of that laborious process of having to put the walls in and create the model, we've got some imports, etc., but a neural network will be really good at doing floor plan recognition, and we've already played around with this, and I think that's going to be a huge time saver, which is great. The other side for me as well is things like optimum start. So when do you kick the heating off, in the morning? It could be anywhere from 4 a.m. to 6 a.m. or even 7 a.m. to hit the set point at 9 a.m. And neural networks, optimum start's a tough problem, but neural networks, particularly trained on sort of hundreds of thousands of TAS runs, could give you a really good BMS control system that would give you that optimum start point. I'm sure there are many other places where neural networks are going to be good, but as I say, I'd avoid the hype. That would be my comment. Sorry, Andrew, you've probably got. Oh yeah, Andrew.
Yeah, I mean,
managed
we'd like to use it.
Code generation.
Yeah, we'd like to use it for the right things. So, for example, writing optimization scripts, or maybe even just having. I mean, I've made a prototype where you can say in free text what you want to happen to your building simulator file, and it'll do it for you. So, for example, you could say, make me internal conditions and make sure that all the classrooms have these many people in it, and it will just do that for you to your TBD. So that area is a really strong area application for it. Whereas we hear a lot of people, around saying. Like we see these new products being advertised saying, it's CFD with AI in it. And you have to be careful there, because the neural networks can be very good at, if they're trained on simulation results, they can be very good at giving you results which look right but aren't right. They can miss subtle nuances in the physics. And the main reason people want AI for CFD is the speed improvement. But our CFD is so quick anyway that it's not really necessary. And that the results that you're getting are physically accurate. You're not going to get these edge cases where you get spurious results and they're very hard to spot sometimes. So yeah.
Andrew, a question for you. How about exposing some of the task functionality via an MCP server? For example, the NG Plus MCP, very powerful and hints at a whole new way of interacting with energy models. That's from David.
Yeah, I mean, it can all be done because our API is it's been baked into the software since we released it. Anyone can do this. If anyone wants to make an MCP server using TAS, it's possible. It's just So if you want details on how to get started with something like that, just let us know.
And the use of AI to aid generation amendment of modeling sounds good. Doug, yeah, absolutely. Workflow orchestration and kind of, just productivity, saving time on things like inputs, checking model outputs, reports. That's obviously a key factor. That's an easy win, one good thing AI is really good at. Duncan, Paul, did you have any comments on that? And then we can wrap up.
Well, I've used it for reading data out of PDFs, so tables in PDFs. It's good at that, getting the data into Excel. So things like plant efficiency data from manufacturers, it often comes in a PDF document. So reading that data into Excel instead of having to type it in. Things like changing bits of software from one language to another. It's good at doing that.
Very good at that, yes. Yes.
Yeah. So it's a tool that you can use, and it can speed up some of the more laborious processes, I guess.
Paul, how about you? Some of the jobs you see on consultancy.
I get sort of different projects different queries on every job that causes problems, and due to the fact that we're very close linked with development and consultancy, when I get a problem, I just get them to sort it out. So anything that comes through, then I will be getting the development team to sort that out for me.
See now everyone realizes Paul is actually head of software development. That's what it boils down to. Or rather, the projects and the problems are head of development. Yeah.
Perfect. We're a few minutes over time. I'll thank you everyone for joining. I'll hand over to Ian for some closing remarks, and then we can wrap up.
Well, no, thank you everybody for attending. You know, I was very surprised at the number of registrations we got for what I thought was one of the lesser interesting webinars that we were proposing. So nice to see there's still a lot of interest in you know, the fundamentals of what we've been doing for what, yeah, nearly 40 years now. So yeah, thank you everybody, and yeah, thanks guys. You know, Nagman, Andrew, Duncan, Paul. Yeah, hopefully people have enjoyed it. Yeah, say, oh gosh, that's nice. Thank you. People clapping. Yeah.
Thank you.
We'll take the applause. Thank you, everybody. Great. Are we all done? Nagman, should we wrap up?
Yep.
Thanks.
Thanks everyone. Bye.
Lovely stuff. Cheers, guys.
Cheers,
Thanks. Bye.
Okay, thank
Cheers.
you.
Bye. Bye.
Bye.